knows about Poisson brackets, we know to evaluate this, we can use the associativities and to decompose into the different Poisson bracket between U and lambdas and so on. Okay, so use the associativity, so we get 9 terms. So 4 terms. I'm not going to try to write it out, but the 4 terms here involves this kind of gadgets. The Poisson bracket between U1 and U2. And we can define K12 equal to U1, U2, U1 minus 1, U2 minus 1. And we can combine actually all these 4 terms into the following way. So I'm really kind of sketching out the steps of the proof, but hopefully from those steps, you can actually derive the rest. It's really just matrix multiplication. In fact, might be a better way to do it, just plug this into Mathematica. Which it does matrix multiplication much faster than human now. Okay, so that's 4 of the terms. So there are 9 terms altogether. So there are other 4 terms. Involves lambda 1, U2, and lambda 2, U1, they're Poisson brackets. So again, we can define Q12, which goes like U2, Poisson bracket U1, lambda 2, U1 minus 1, U2 minus 1, and combine them into basically Q12 L1 minus Q21 L2. So really, here the proof is really by brute force, that multiplying all the 9 Poisson bracket out. And putting everything together, so there are 4 terms here, looks like this, and there are 4 terms like this. And finally, there's a term looking simply involving the Poisson bracket of lambda 1 and lambda 2, the eigenvalue itself. Okay, so that's basically saying that if you evaluate the Poisson bracket L1, L2, it's basically equal to U1, U2, lambda 1, lambda 2, U1 minus 1, U2 minus 1, and plus the R matrix equation, R12, L1 minus R21, L2, where the matrix R12 is basically equal to Q12 plus L2. So basically proof 1. So if we know they commute, as we assumed just now, then this term goes away, then we basically prove our statement kind of going one way. So to show the equivalence, we need to prove it the other way. Hopefully it's faster. So prove the converse suppose we are given, so basically, suppose now we are given R12 L1 minus R21 L2 equal to L1 L2. Okay, so we want to show, so suppose then we consider basically consider L1 and L2 and in their commutation. So by some manipulation or just by systematic deduction, that for low power of n and m, then you can do it prove by induction. We can express into the following, whereby the A12 and T12 and M minus P equal to 0, M minus 1, Q equal to 0, M minus 1, L1, M minus P minus 1, L2, M minus Q minus 1, R21, L1P, L2Q. Okay, but the nice thing about it, whatever this is, not just expression, but let's just take a trace over the space 1 and 2. So you take trace of those two guys, and we have it, because that's the point, that the trace of the Poisson bracket, sorry, trace of the commutator is again 0. Yeah, so take a trace over both sides, and we know that the trace of this, those are both commutator, and whatever junk you have here, that gives you 0 anyway. So that basically tells you that if you trace this, that'll give you 0. Done. So those charges are basically commuting. So basically, all the conserved charges are going to come from the eigenvalues of the Lax matrix, and or more precisely, they are actually like a symmetric polynomial of the eigenvalues you have for those Lax pairs. So that's why once you have a you can actually construct it instead of trying that aimlessly to construct what are the the conserved charges when you are given a classical mechanics system, but instead if you can solve the auxiliary problem that to construct what are the Lax matrix or Lax pair, then you basically solve the problem by equivalent. But it's just that generally there's very hard to find a one-size-fits-all recipe for all the mechanical systems you have. So that's why, in fact, like a very few kind of very special classical integrable system, like for example things like Toda system, like elliptic or various kind of Colliger or Moser system, that they play a very kind of treasure important role in the kind of modern high-energy theory research. So, I mean, of course, I won't be able to get to talk about the quantization about those, but hopefully in the afternoon, when I kind of, if I have more time, I can talk for some example that actually tell you what exactly the Lax matrices for those guys actually look like. Okay, but I think we can stop here for lunch. All right.